Namaste. In this session, we will study how to construct data set from different formats. We will cover formats like CSV or in-memory structures from NumPy and Pandas. We will also study how to construct data set objects for images and text. So, let us start with CSV data. So, the data that we use in this session is taken from Titanic passenger list, where we want to build a model to predict the likelihood of a passenger's survival based on their characteristics like age, gender, the ticket class, whether the passenger was travelling alone, etc. So, let us install TensorFlow 2.0 and import essential libraries. Let us download the train and test data from Titanic dataset. The Titanic dataset is available in TF datasets. We set the precision to 3 so that the numeric values are easier to read. Let us look at first few examples from CSV file. So, you can see that the label survived is the first column, it is either 0 or 1. Then we have features or characteristics like gender or sex, age, number of siblings or spouses that were travelling together, then the parch, the fare, the class, deck, the embarkation town, and whether the traveller was alone. We will load the data using Pandas and pass the NumPy arrays to TensorFlow. If you want to scale up to a large set of files, then we will have to use make_CSV_dataset function, which is currently in the experimental version of TensorFlow. We separate the label column, and as we said, there are two labels, 0 or 1. Let us read the file and create a data set. So, here we demonstrate the make_CSV_dataset function, which can be used for large data sets. The Titanic dataset is pretty small, but still we decide to demonstrate make_CSV_dataset function with Titanic dataset, because this will be applicable for large CSV files as well. Here we are taking a small batch size intentionally so that we can examine the examples in each batch. We specify the label name, specify how null values are predicted, how null values are specified with question mark here in this case, and number of epochs we set it to 1. We construct the training data by giving the training file to get_dataset function and test data by providing the path of the test file to the get_dataset function. the get underscore dataset function makes a dataset from CSV file and returns the dataset. Each item in the dataset is a batch represented as a tuple of examples and labels. The data from the examples is organized in column based tensors, each with as many elements as the batch size. Let us look at one of the batch. You can see that since we have set up the batch size to 5, for each of the feature we have exactly 5 values. So, you can see that each feature is organized as a column based tensor. So, you can see that there is one tensor per feature, one tensor for sex, another for age and so on, and in each of the tensor you will find exactly 5 values, because we have a batch size of 5. We can specify the columns that we want to use to construct a data set and pass that in the select underscore columns argument of the get underscore dataset function that we wrote earlier. And since we chose only handful of the features, we can see that there are only those many features that were selected are shown here. A CSV file can contain a variety of data types, and typically we want to convert the mixed type to a fixed length vector before feeding the data into the model. So, TensorFlow uses a construct called tf.feature underscore column for such kind of conversions. If our data is already in a numeric format, we can pack the data into a vector before passing it off to the model. So, we select columns which are numeric, we specify the default values and we batch the data set. We can look at the example batch and the label batch. We will pack together all the columns and we apply this to each element of the data set. We apply the pack function to each element in the data set, and we can see that we have a feature metric or a 2D tensor of features and a 1D tensor of labels. If we have mixed data types, we may want to separate out the simple numeric features. The tf.feature underscore column API can handle this, but this incurs some overhead and should be avoided unless really necessary. Let us define a more general preprocessor that selects a list of numeric features and packs them into a single column. We take the numeric features and pack them and now you can see that all the numeric features are packed into a tensor, whereas the other features are kept separate. We need to normalize the continuous data, and one of the ways of normalizing is by using a z-score normalization that we studied earlier. Let us see how to do the z-score normalization on the numerical data or on continuous data. So, we first get the mean and standard deviation of each continuous column, and then define a normalized function that centers the data. Now, we create a numeric column with tf.feature underscore columns dot numeric underscore column API and pass the normalization function as an argument. The normalization will be run on each batch. Let us put all the numeric columns in the dense features and pass it to the model. So, you can see that the numeric layer has normalized data for each of the numeric features. Let us see how to handle the categorical variable. We use tf.feature underscore column dot indicator underscore column to convert each categorical variable into a one hot encoding. So, to begin with, we construct dictionaries of values in each of the categorical variables. For example, sex has male and female in it, class has first, second and third in it. There are A to J decks, then there are few embarkation towns, and alone has two values, yes or no. Then we take each of these categorical variables along with their vocabularies and convert those categorical variables into indicator columns using the vocabulary list. Let us check out the categorical columns that are created as a result of this exercise. So, we can see that there are indicator columns that are created from this exercise. We also create a dense feature layer out of the categorical columns, and now what we can do is, since the categorical columns are converted into numbers, we can combine categorical columns and numerical columns into dense feature layer and pass it to the model. You can see that the preprocessing layer, which is a dense feature layer, is passed to a model. So, this is how we handle the dataset creation using CSV and the preprocessing. Let us check out how do we do shuffling and batching. So, we can simply call a shuffle transformation on the training data by specifying the buffer size. and then as usual what we can do is you can evaluate the model on the test data and see the accuracy. We can also check out the model predictions and compare that against the actual outcome. We will be doing more and more of model training and evaluation in the subsequent sessions. So, we are not giving much stress on that particular part. In these sessions more stress is given on creating input pipelines from multiple sources. Let us look at another source of creating input pipeline, this time with NumPy. So, here the data is stored in NumPy array and we want to convert and we want to construct the data set from these NumPy arrays. Let us look at the broad steps and then you can go through this Colab on your own. So, we read the NumPy array where we have fashion MNIST data set which is stored as NumPy array. We read that we get train underscore examples, test underscore examples, train underscore labels and test underscore labels corresponding to training examples, test example, training labels and test labels. We use from underscore tensor underscore slices from the dataset API for constructing data sets from NumPy arrays. Finally, we can do shuffling and batching of the training data set, whereas on the test data set we can apply let us say batch transformation, and then you can build a model and evaluate its accuracy through and evaluates its accuracy on the test data set. Let us look at how to load or how to construct data sets from pandas data frames. Here we have a data set provided by Cleveland Clinic Foundation for Heart Disease. There are several hundred rows in the data set. The data set is in a CSV format. Each row describes the patient and each column describe an attribute of a patient. We will use this information to predict whether the patient has heart disease or not. So, let us look at the steps to create a data set. We use dataset dot from underscore tensor underscore slices to create the data set from the pandas data frame. So, in NumPy and pandas where the data is sitting in memory, we use from underscore tensor underscore slices function of dataset API to create data sources. Let us try to understand how to create a data set from an image data set. The image class is provided in the directory name and we have multiple directories of the images. So, let us see how to create input data pipeline for such a data through this example. So, here we first download the file. You can see that there are directories like Dandelion, daisy, tulips, which contain images of the respective flowers. And there are 3670 images in all, and these are top 10 image paths. So, you can see that there are few images of dandelion flower, some images of sunflowers, some of roses, tulips, daisy, and so on. Let us look at couple of images. We will first assign the label to each of the images. And for this, what we did is we took the string labels and assigned an index to each of the labels. So, instead of strings, now we have converted those strings into numbers. We can read the image using tf.io.read_file function by providing the image path, and we can decode the image into an image tensor. So, we can see that the image tensor is a 3D tensor with shape 240 by 380 by 3. There are 3 color channels and each image is of the size 240 by 180. We will resize each of the image to 192 by 192 and we normalize the image by dividing each pixel value by 255. So, we wrap all this transformation into a simple function called preprocess_image, where we first decode the JPEG file, resize the image and then normalize the image in the range between 0 to 1. And what we do is we put load and preprocess, we wrap it in load underscore and underscore preprocess underscore image function. And let us look at some of these images after preprocessing. Let us see how to build a tf.dataset from these images. So, we first construct a dataset of paths. All the paths are in memory. So, we use from underscore tensor underscore slices as we were doing earlier in case of NumPy and Pandas datasets. Now, we create a new dataset that loads and formats image on the fly by mapping preprocess underscore image over the dataset of path. So, we use a map transformation and apply this particular function on each and every image in the dataset of paths. Let us look at some of the images from the dataset. We look at first 4 images. You can see that there are images along with their labels. There are images along with their descriptions. We build dataset of labels next using from underscore tensor underscore slices function. We use dataset.zip to assign label to each of the image. And you can see that each image is of the size 192 by 192 by 3 and each label is a scalar. Now, in order to train a model, with this data set, we want the data to shuffle, we want to first shuffle the data, then we want to batch it and then repeat forever, and we want to make sure that batches are available as soon as possible. So, we use shuffle transformation for shuffling the data by giving sufficient buffer size. Then we use repeat for repeating the data set epochs after epochs, specify the batch, and we use a prefetch function that lets the data set fetch batches in the background while model is training. There are a few points to note here. The order is important. A shuffle after repeat would shuffle items across epoch boundaries. Some items will be seen twice before others are seen at all. A shuffle after batch would shuffle the order of the batches, but not shuffle the items across the batches. We use buffer underscore size of the same size as the data set for a full shuffle. Up to the data set size, large values provide better randomization, but they need more memory. Shuffle buffer is filled before any elements are pulled from it. So, large buffer size may cause a delay when your data set is starting. The shuffle data set does not report the end of a data set until the shuffle buffer is completely empty. A data set is restarted by repeat, causing another wait for shuffle buffer to be filled. So, we use the dataset.apply method to address the last point, and we fuse it with shuffle and repeat function as seen here. Finally, we pipe the data set to the model and train the model. The MobileNet expects its input to be normalized to either the MobileNet expects the input to be normalized to -1 to +1 range. So, we convert our data from 0 to 1 range to -1 to 1 range. We define a change underscore range function and apply that on each element with map function. The MobileNet returns a 6 by 6 spatial grid of features for each image. We pass it a batch of images to see the output of the MobileNet. You can see that it returns 6 by 6 spatial grids. Finally, we build a model wrapped around MobileNet and global average pooling 2D to average over those spatial dimensions. And then use a dense layer with softmax activation as the output layer. We can see that it produces output of the shape 32 by 5. We compile the model to describe the training procedure. And train the model. For the demonstration purpose, we will only run 3 steps per epoch. See you in the next session. Dhanyavad.